Okay, so let's, I think if somebody else joined, then we can update them. So did you manage to attend Sunday class?
Yes, I did. It was about optimization techniques, wasn't it?
That's correct, yeah.
So it was, yeah.
Yeah. So we're going to start today, then we start with the learning rate scheduling, and
Uh,
we finish the chapter.
yeah, okay.
I think I'm not sure, they didn't do the Adam or an Adam, or did they do it? I don't remember it.
To be honest, I joined without knowing which topic it was,
Oh,
and I already, well, I haven't stayed until the end because I kind of studied that topic by myself before.
okay. No, I remember now. I think they did finish Adam and an Adam. So what we're going to do is we are going to start from learning rate scheduling, and we finish the chapter.
Yeah, okay.
All right.
Yeah.
And it's the 5:76 past the hour. So maybe let's say we'll meet at 10 to the hour.
Sorry, Ivan.
Is what time zone you are in?
Oh, I'm UK time zone,
Okay.
so 6
So
p.m.
okay, fantastic. So we're gonna meet at 10 to 7.
Yeah, okay.
Okay. So I think I see Francesca joined in. Hey, Francesca.
Hi, how are you?
I'm very well, thank you. Have you finally moved over to this
Yes,
side of the pond?
I'm in London actually. Yeah.
Oh, welcome to the London.
Thank you.
Cool. So what we are going to do is we are doing the chapter 11, and we're going to
Right. Yeah.
read from the page 352, which is a learning rate scheduler. Learning rate scheduling, and all the way finish the chapter. The last topic of this is, let me go to the end, max norm regularization. Okay. And
Okay.
we will meet in 40 minutes, 10 to 7.
Okay. Great. Thank
All right.
you.
I'll talk to you then. Cheers.
Bye.
Bye. Okay, everyone. It's 10 minutes to 7. We should start. I'm going to share my screen. Desktop 2. Do you see my screen?
No.
How about
Now I can see it.
Okay. Okay. So that's where we're going to start. We finished the optimizer in the last Sunday call with the US guys. We're going to start with the learning rate scheduling. Just before it, this is the table where they have defined the different optimizers and the speed of the convergence, as well as the convergence quality. Quality in a sense like how close the optimizer ends up to the optimal solution whatsoever. It looks like the last 4 are more or less have same star. Star means 1 is bad, 2 is average, and 3 is the good. So when we see the convergence speed for RMS, prop, Adam, Nedum, AdamX, all of them are very good. And the sorry about that. And the quality is again average to best for last 4. I guess it all depends upon the data set you have whatsoever. Okay, so the next one which we're going to discuss is learning rate scheduling. So this is more about again, this is a hyperparameter tuning, or perhaps like the what learning rate what we should use. That's this is all about. As they define in this picture that if we have a too high learning rate, we may just go off the path. If it's too high, and if it's too small, so it's going to go slow, very slow, so it's going to go too long to get into the optimal solution. Eventually it will reach the solution, but it will take too long, too many epochs to get in there. We may have not too way high, but high, so it's gonna our system will go faster train, but afterwards it's going to go bounce off the optimal solution. So if eta is too high, we're going to get too suboptimal solution, and that's what we're looking actually. So we're looking as a purple line, which is it goes down in here, and then up to this point, rather than flattening it out, it keep going down all the way up to here, and we get the best results. So what actually this is trying to say is trying to say that we need some sort of like learning rate which is high enough initially, so that we just drop down, and then at this point in time we need to do some adjustment to a learning rate so that it keep learning rather than it's just bouncing around. So that's the whole idea of this paragraph. So how they do it, there are different ways of doing. One way is called a power scheduling. So power scheduling, if you look at the function, eta of t is equal to eta naught. So eta of t is the eta is your learning rate. So learning rate function of t. I'm not sure t is time or what. Anybody has an idea what t would be in this case?
Isn't it iteration?
Number of iterations.
The current iteration, or I think.
The S are the steps. So S I know is the steps, but I'm not sure T. He hasn't defined here T. Anyway,
No,
so
what I had in mind is S is the total number of steps and T is the current step.
okay, so you mean S is total number of steps and T is your
Current
end
step. Yeah,
Okay.
end step. So yeah.
End step. Okay, yeah. So eta naught is your initial learning rate divided by 1 plus T is, as you said, nth step divided by number of steps, total number of steps, all raised to power C. C is generally set to 1. It is again a hyperparameter you can tune in, but at this stage, let's keep an C as a 1. So what he's saying is it's a power scheduling. That means if you put the numbers in, your learning rate will be first eta naught by 2. So that means it's decreasing fast. And then it's going to be eta naught by 3, eta naught by 4, eta naught by 5. So looks like the learning rate is reducing first very fast, half, 1/3, 1/4, and then it start reducing so on and so forth slowly. So that's how he's adjusting. That's the one scheme of the learning rate. Oh, sorry. The next one is the exponential scheduling. So set the learning rate of eta of t is equal to eta naught 0.1 raised to the power t by s. So all in all, what it's saying is every step it's gonna every s step is gonna change by the power of 10. So that's the exponential scheduling. Another one is a piecewise constant scheduling, and what it says is that for let's say for first 5 epoch, you have a learning rate of 0.1, and then from 6 to 50, you will reduce it to 0.001, and then maybe a next 25 or 50 or whatever number of epochs you pick up, you change that learning rate to some other value. So what you do is, what you're doing in this case is you're defining the learning rate for number of epochs. So that's your piecewise constant scheduling. And the next one is a performance scheduling. Performance scheduling is measuring the validation error every n step. So what I think one of the chapter like this, Leslie Smith's chapter I was looking at, and this is the paper by Leslie Smith, where he has, in this paper, he has defined what he's talking about here is, if I open it, so basically in this paper, he has defined that what he's saying is when you observe the learning rate, the validation error, this is the, just 1 second if I can. Yeah, so this probably is more clear. So we have test loss, which is this test loss, and this is our training loss, and this is our test accuracy. So what he's trying to say in this paper, is a good paper, everybody should read. He says this gives us an idea. This paper gives an idea how the learning rate, how we should keep an eye on the test versus training loss, and that gives us an idea where to change the learning rate. So for example, if I go back in here, sorry, in this paper, not in this paper. I think it's his paper. So let me see if he has defined it. Yeah, here. So that's where he's saying that if that's your training data, that's your test data, and then what you're looking is you're looking this is the optimal solution. So your learning rate will learn here, and then it afterwards up to this point it's the underfitting, up to this it's a overfitting. So you probably looking this dip around here. So this is your optimal solution. So that's what he is defining, that how you should look training loss versus the test loss, and try to find out this point so that you pick up the learning rate, which gives you this optimal solution, and then you use that learning rate. Anyway, I'm going to go back to paper, and I think performance scheduling is something similar of what one cycle scheduling is. And one cycle scheduling is what I just defined. There is another thing which I want to show you is Jeremy's paper. Yeah, so if you guys are aware, Jeremy Howard uses the Leslie Smith method, and what he has this like LR find method, and what it does is like it's plot your errors, so learning rate versus a loss, and then you can see it's dipping down in here, and then all of a sudden from here onwards your loss start increasing. So that was your optimal solution. And what does it do is what does actually Jeremy mentioned, that we should pick a learning rate between this point and this point. And he usually picks up something where it's a deep dip, which kind of like 10 raised to the minus 2 divided by 10 around here. So he's going to pick something in here. And that's what he found, that's the most optimal learning rate. And then you just pick up this 10 raised to power, let's say here, 10 raised to power minus 3 is your optimal learning rate, which you take away and then start using in your model. And that's exactly what he is defining in this one cycle scheduling paper. And then what he was saying is with this method, he could get this like 91.9% validation accuracy as compared to 90.3 accuracy. He got this accuracy in 100 epoch, while the other author previously on a CI FAR 10 image that said this was the accuracy after 800 epochs. So that was the one cycle scheduling. Anything you guys want to discuss? Anybody?
Not really.
Okay. All right. Let's move on then. So how do you implement in Akiras? It's quite straightforward. You mentioned whatever your initial learning rate, and then decay of your what decay to a learning rate it's going to be, and then that's pretty much it. That's the one way of doing. And then exponential scheduling and piecewise scheduling are quite simple too. You first need to define a function that takes the current epoch and return learning rate. So this is like exponential scheduling defined. That's your function. Number of epochs you're giving, that's your initial, and not eta naught, which is your initial. If you don't want to specify the hard code value, you can rewrite this function in here where you're going to pass 0.01. But anyway, so that's your function. All you're doing is 0.01 multiplied by 0.1 raised to the power epoch divided by 20. And I think that 20 is the number of steps, all steps. So let's go back here. Let's check the, this is the exponential scheduling. So eta naught, which is your 0.01, and multiply by 0.1, that's this term, raised to the power epoch, which is t, that is, okay, so t is the epoch. So epoch would be, I think, epoch number. So you're right when you mentioned which step. So which epoch step we are giving. So, and for each epoch, this your learning rate will start decreasing slowly. So that's the implementation of the exponential decay. And I think piecewise, he said you can do the same way. Yeah, and this is exactly the written same. This guy, he just wrapped it up in here. Okay, so that's that. Let's move on. Okay, so what he's talking here next is learning rate scheduler callback. Okay, how are you going to use? So this is your function defined. How are you going to call this within your library? So you will be defining this learning rate scheduler object, and you will be passing this object into a callback when you fit the model in here. Does this make sense?
Yeah.
Yeah, okay. So it's quite straightforward. Okay, so that was a callback, and next one is exponential. So what is the schedule function can optionally take a current learning rate as a second argument. Okay, for example, the following scheduling function multiply the previous learning rate by which result in the same exponential decay, except the decay now start at the beginning of epoch 0 instead of 1. Okay, so I'm not sure what he's talking about here. So let's read this. The learning rate scheduler will update the optimizer learning rate attribute at the beginning of each epoch. Updating the learning rate once per epoch is usually enough. But if you want it to be updated more often, for example, at every step, you can always write your own callback. Okay, so what he's trying to say here is like we generally, this function, if I go back, this function we have written, we saying we're going to change it to every epoch, but he's saying if we change it to every step. So step, I am assuming, is going between the layers. Is that correct?
Maybe every batch, like.
Okay.
Yeah, because when you are writing PyTorch, you have like that step at the end, don't you, when you do backpropagation?
So batch would be, if we have, let's say, 100 items, and then we are creating, let's say, batch of 32 or batch of 20, let's say, for the simplicity. So we're going to have 5 iteration or 5 different batches. So we are saying if we want to, instead of doing a one epoch of 100, changing a learning rate on that, we can change on batch of 20. And then if we want to do if that's what we want to do, we can do it. Is that correct understanding? S is the batch?
No, I'm not sure.
Okay, so step, this is what the confusion is.
Yes, I think that's correct what you said, because what he's saying, if you have a lot of examples, so for example, if you have like, I don't know, like 100 epochs, then after each epoch, you are doing backpropagation. So if, for example, you do like 7 epochs or so, then your model is already trained and you want to drop the learning rate. So yeah, I think it's like you said.
Okay, so batch, let's take the S as the batch at this point in time. Okay, so that's that. Let's move on to the next. Okay, and this one is piecewise function. So all he's doing is like just counting the epochs. If the epochs are still less than 5, then you have value 0.01. Otherwise, if the for the 6th epoch, 6 all the way to 14th is going to use this one, and then from 15 onwards, that's the value going to get returned. And I think that's the function defined. And in the callbacks, and so for performance scheduling, use the reduce LR on plateau callback. For example, if you pass in a following callback to a fit method, it will multiply the learning rate by 0.5 whenever the best validation loss does not improve for 5 consecutive epochs. Otherwise, options are available. Please check the documentation for more detail. So this is something else. He's saying performance scheduling. So basically, the piecewise is different. Here, it's more of like looking at the performance of the model. I think the patience 5. So this is what he is explaining, that you can check, even your library can check if the performance is good enough with the learning rate which you are specifying. I think that's what I got from this paragraph. Okay. Yeah. So that's fine. So documentation, I haven't practically done anything. So it would be interesting to see. Okay. So lastly, offer an alternate way to implement learning rate scheduling, defining the learning rate using one of the schedules available in this. When pass this learning rate to any optimizer, the approach update the learning rate at each step rather than at each epoch. For example, here is how they're implementing the same exponential scheduling at the exponential decay. Okay, so that's exactly what we were discussing here. Learning rate scheduler. This is exactly what it was. The number of steps in 20 epoch is best size equal to 32. S is 20. Yeah, I need to look a little more closely. I don't have a clue what's going on here.
Yeah, that one seems to imply it's just the total number of training samples you're going to use in 20.
Arshad, you're far away from your microphone.
Every single one of the ones in the training set. You're doing 20.
Hey, Arshad.
Yeah.
You're far away from your microphone.
All right, sorry. Microphone problems again. Yeah, give me 1 second.
Hello.
Is that any better?
Not really.
Okay, I'm going to switch over to my headphone.
Okay.
Yeah, the next machine I'm trying to set up at home, because it's got a 1080 Ti. I've been trying to use it, but it's not great.
I can barely make it what you're saying.
Before it was better, although you had more background noise.
Is that better?
Oh yeah.
Yes.
Better.
Yeah, sorry guys. Yeah, I'm trying to still set up this machine at home, which is a Linux machine. And all the hardware is kind of all, not playing very nicely. Anyway, yeah, all I was saying was, yeah, where that calculation for S equals just is the total number of training samples in 20 epochs, isn't it? Because they're saying the length of the training set times 20, because they're doing 20 epochs, which is a bit strange. Yeah.
That's a total number of training steps, like 20 by length of training set and divided by 32, which is a batch size. So this S is a total number of training steps in 20 epochs.
Oh, is that Python? So is that giving back an integer because it's got 2 divides or something?
I thought it was comment.
Yeah, it looked like Python doesn't do // does it? I keep forgetting because I'm so used to Java and okay, that makes sense then. Yeah, that's the number of batches, batch steps. Yeah.
What do you mean by batch steps? Like batch size is 32. So
yeah, so as this the other person was saying, if you look at that formula, it's 20 times the length of the training set. So that's the total number of training inputs that you're going to give.
Yeah.
Because because you're running 20 epochs, but then you're doing 32, a set of 32 per batch. So that's why it's dividing by 32. Although it's using that // so I'm not sure. Is that like integer division or something?
Yeah, that's integer.
Yeah. So the step is okay. So what?
So the step is batch, but what was it before?
I think it's like, so if you have, like, if you're training, like if your set is 1,000 images,
yeah,
and you're dividing in batch size of 32, but the length for that epoch. So if it's 2,000 images, like the length, your X train would be like 100, and so S is like the total divided by the batch size. It would be like 2,000 divided by 32.
Yeah.
Is that right?
Yeah. So so your step is more than the batch, like 32. So it's like it's a.
I think it's like the total divided by the batch.
Yeah.
No, so in this case, the step is the amount of batches what you have. But could we go back?
So this let's say the step, like let's say you have 1,000 images, you have 20 epochs, and then batch size of 32. So step size is 625.
That would be.
Yeah, I think that's correct. But so what was we talking about before? Because before I thought it was also kind of the same calculation.
Yeah, so before S, they never defined. So this is interesting. Like in here, when we talk about here, it says the step S. So basically, he never clarified what the S is. He never even mentioned what the T is. So S is just a hyperparameter. So it says step S. So that's the first time in here he started defining S.
Yeah, but S is like a period in which your learning rate degrades by some factor. Like it was explained, I guess, a little bit before, in where he defined that exponential decay function.
In here?
Next page.
Next page. Here?
Okay, so look, he is defining this exponential decay function with epoch divided by S. So it's even was said somewhere that learning rate will decay by factor of 10 every S steps, for example, to every 20 steps of this scheduler. And how often do we step the scheduler depends on how we define this function. So we can step it every epoch or every like 5 epochs or every batch. And I think that the best way is to plot it like it's done in Jeremy Howard's paper, and to see how many iterations we done and how many. Like here you can see the number of iterations against learning rate, and it's clear how it changes through training. But here I'm not really that much familiar with Keras. I'm like more PyTorch user.
Yeah, I think you mentioned it. So this is good example, because I think somewhere he mentioned, sorry, that this is, I think in the end he said, of course, S and S is a hyperparameter you can tune in. I think somewhere he mentioned it. So you're right that in here we're defining S is 20. In this case, we are defining S is this value. So perhaps this is one of the hyperparameter which you will be tuning in to find the best learning rate, I guess.
Yeah.
Okay,
yeah,
let's
I mean,
move
the
on.
confusing aspect of it is that the input to that original exponential function that you had, it had the original learning rate, LR0, the number of steps, and then within it was the second function, which took as input the epoch. So he's going to all that trouble that it seems like in Keras, there is a learning rate per epoch. And that's all this is doing, is calculating for each epoch the learning rate.
Mm-hmm.
Because if you look at what that's doing, it's calling exponential decay with those two parameters, the line near the bottom,
Yeah.
just where your cursor is, with those parameters 0.01 and 20, and that's fixing those two in the inner function.
Correct.
And then the inner function is returned, but the only input to that is the epoch. So yeah, I mean, it's confusing because he's, when he's doing Jeremy Harris doing that graph, it's almost like every batch something's happening to the learning rate.
Yeah, but that's a different schedule. In Jeremy Howard's paper, it's one cycle schedule, and there step is done every batch. But in other schedulers, it might be done however you want. Like in that piecewise schedule, we done it like every some epochs predefined number, and here we can manipulate our decay rate by setting this hyperparameter S.
It was my misunderstanding, because I thought these learning rates were going to be per batch, but it looks like these particular ones are per epoch, right?
Or epoch, and perhaps like he has a smaller unit of the step S. So instead of like you're going to do on per epoch, you can have a step as such, where you can decide if at that stage you want to tweak the learning rate whatsoever. Another hyperparameter. Okay, so let's move on. Good discussion there. Okay, so the next, what he was talking is avoiding overfitting through regularization. So in a deep learning, we did regularization L1 and L2, I think in chapter 4. And what he's saying is you can do regularization in deep learning as well. Just specify this L2 regularization, and it's similarly, I think it's a L1. What's he saying in here? One question I have is like L2, so L1 is the regularization where we chop off the corners where the weights are very small. What does the L2 regularization do? Could anybody explain to me?
Yeah, it's like we add extra regularization term to our cost function, which is proportional to the L2 norm of of weights which we are decaying. So the higher weights our model learns, the higher loss function we get. So the model learns to have this weights like smaller in general, like regularized by L2 norm.
So if we have like higher weights done by the model itself, so that we punish it by adding the regularized L2 regulation to the loss function.
Yeah.
Okay. Okay, so he's just saying you can apply the regularization just dot L2 and then this passing this parameter in here. Similarly with the L1, so that's pretty straightforward. Okay, so in here, since you will be typically want to apply the same regulation to all layers in your network, as well as using the same activation function and the same initialization strategy in all hidden layers, you may find yourself repeating same arguments. This makes code ugly and error prone. To avoid this, you can try refactoring your code to use loops. Another option is used to Python func tools partial function, which lets you create a thin wrapper for any callable with some default arguments. Okay, so all he is doing is nothing but we are applying this L1 or L2 or L1, L2, both regularization. So instead of we keep on applying this, we have defined a wrapper function, which is like from func tool. So partial regularized dense, we inherit from the dense layer here. And all we are doing here is just kernel initializer is this, and kernel regularizer is this. Oh, this is part of the part of this. So this is the object we are defining, and within this object, first argument is this, second argument is this, and third argument is this. And then within the model itself, we, instead of using a dense layer, we're going to use regularized dense layer time and again. So this regularization will call automatically instead of calling a dense layer and then regularization and dense layer and the regularization. So that's what he is doing here. Okay, so anything you guys want to discuss in here? Okay, so I'm gonna move on to dropout because we are running out of time. So dropout is explained very well in here. It's the regularization method, and what I understood from the from this whole text is that your architecture or a neural network could be clever enough to start remembering stuff. So what we do is we randomly delete the nodes for each epoch. So there is a probability that for a next epoch, you have this, and this, not the output one, this, and this input is cut off. And what does it do? It regularizes the network, not too dependent on the previous node, but to keep an eye on all the input signal it's receiving from all the other nodes below it. So interesting enough, that gives the accuracy boost. And I think in here somewhere he said by regularization it gave a 2% of a boost automatically. And the idea is that stopping your network to overfit. That's the whole idea. And then all you do is when you use the regularization, I think you just mentioned here, keras.layer.dropout rate is equal to 2. So 20% of the time, the neurons will get stopped on each epoch randomly. So that's the whole idea of a dropout. One of the important point he mentioned in this text was that when you use the dropout only during the training time, you don't use the dropout on the testing time. So, however, the input which you are getting at the training times are half. Let's say you have a 50%. If you have done the 50% phase equal to 50%, that is half of your neurons for each epoch is going to be not producing anything. So you need to divide the input weight of the testing by half, just to have your training and a test data on the same scale. So that's one thing which we want to keep in mind. Correct me if I said this thing wrong here. It's very important for me to understand as well if I understood this correctly. Are you with me on this point?
I guess that's what you said is correct, but it's usually done, I believe, a bit different way. Like you scale up the activations after dropout. No, like in general, you scale up your activation after dropout to make sure that they will be distributed like the activations without dropout.
Okay, so
does it make sense?
Yeah. Instead of dividing, we just multiply by 2. So
yeah, we will multiply it at training, not divided testing.
Okay. And just one question with regard to that. Is it we multiply the weights by 2?
No, just activations, like output of the layer.
Okay, so the output of the probabilities.
Yeah.
Okay.
Like of each layer. If you have multiple layers, you need to multiply after each dropout. I think it's done internally in this dropout layer. In
here. Okay, after this, so we have dropout, and then after dropout we have the activation, and then you're saying then you multiply by 2.
Yeah, but I think it's actually done inside the dropout layer in Keras. You know, you don't need to do it manually.
Okay, we don't do manually; it's done in here. Okay. Yeah. However, when we apply the dropout layer, you mentioned after the activation. Isn't it sequential?
No, it doesn't matter. Like we can apply dropout layer between any layers of the neural network if we want to regularize. Like this first dropout is applied just after flattening layer, so it's applied to inputs. So we don't see 20% of the input every time. We like don't see 20% of the input feature.
Yeah, that's correct. But I was looking when we multiply by when we scale it up to the normal.
Like every time when we do dropout, we need to scale up.
At which
scale
stage?
Back up. Like I think it's done just inside this dropout layer. Like you dropped this 20%, so you need to scale up to get back that magnitude of activations.
Is this what they're talking about in the last paragraph on the opposite page? So they says there is one small but important technical detail.
Yeah.
That you have to change the. I mean, they're saying you have to change the weights because.
Yeah.
Sorry, it was the previous page, I think.
Previous here.
Yeah. So just below tip, where it says there is one small but important technical detail. Suppose you drop 50% of the neurons, which means that in production you'll have more neurons connected. So you'd have to somehow adapt the weighting given because you're seeing more data.
Yeah. Yeah. I think I got it. I was just looking for this weights by like what do you enhance? So that's enhancing the weights by 50%. Yeah. for the rest of the neurons then,
Well,
which is going forward.
No,
In the next
so
layer, yeah.
this is done on testing, so it's for all neurons, which goes to another layer.
Yeah. Okay, so
this is the final output, isn't it? So during training, because it will have used dropout, but when you use it finally, dropout will not be there. Not quite sure how that bit works because I'm not really a Keras kind of person.
What I'm trying to get in is, like, I think I understood. So weight goes by 50. Let's say if we have 20%, if we have a 20% of rate dropout, so we're gonna enhance the weight of the remaining neurons by some percentage. So no, is it 20% we enhance, or what are
No.
we going to do?
Basically, what that means that we will have. So you have like a flattened image, which is like 784 pixels.
Yeah.
And when you pass through that dropout, you will have 80% of those pixels. And this will be on the training set. So you will have like 20% of those pixels randomly taken away.
Yeah.
And when you are testing, you will have all 100% of the pixels.
Yeah.
But each of those pixels will have 80% of their value. I think that's how it works.
That's correct.
Yes, that's one way to do it. And look, just alternatively, we can divide each neuron's output by the key probability during training. That's what I was talking about. So it just seems more intuitive to me, and also how it's done in practice. Like if you divide each neuron output by this key probability, which is 1 minus dropout probability, you have like amplify your outputs of each neuron.
Yeah, that's correct. Yeah. And then he mentioned in here, more generally, we need to multiply each input connection weight by keeping probability 1 minus p after training.
Yeah.
All right. Okay. So I'm going to quickly zip through. I think there is a homework class after this. So that was dropout, and there is another method of a Monte Carlo dropout. And Monte Carlo dropout, I think our discussion falls very good into this Monte Carlo dropout. And so instead of, I think it's it mentioned in here, I forgot. So this is like I gotta read this. So first the paper established a profound connection between a dropout networks. So that is a neural networks containing a dropout layer before every weight layer, and approximate Bayesian inference. So in a sense, what they're trying to prove is that the mathematical proof of a dropout by giving the Bayesian inference to it. So that's one thing they're talking about here. And then I think one of the interesting aspect, okay, I'm going to talk about the practical aspect, which I understood from here. What I understood from here is that it's they've gone through this example, and in here in probabilities, I think somewhere here. So there was one probability. It was used the this example was used where the probability it gave 99% predicted probability, and here is the 99% of the probability it gave for the class which we are looking here. With the Monte Carlo simulation, it gave a different probability, and it came around 0.62 for the class which we are defining. And then it gave some probability for other classes as well. So what they're trying to prove in here is that when we work in a medical imaging and so on, I think the method of a Monte Carlo is better, so that we have an idea what exactly is the probability, rather than having a model overconfident. So that's the gist of Monte Carlo dropout, and the whole text I got out from here. And anything you guys want to discuss on a Monte Carlo dropout? And quick question: do we use Monte Carlo dropout? I haven't heard people using it. I just heard dropout. So I'm just curious to know whether we use it or not. Okay.
I was a bit curious about Monte Carlo dropout because I did not fully understand it. It was talking about it, but it's kind of like assembling multiple dropout layer selections, and I could not fully understand it. Well, was it something like to use a dropout layer on an actual test set and use it for a bunch of times, selecting different neurons and then averaging it?
Yes, exactly.
Is
It's like you get for each prediction, like you can make 100 prediction, and you will run this prediction with a different model every time, because you have a dropout active when you do these predictions. So yeah, it's like a random forest for neural networks, I guess.
And one of the important aspect I got from Monte Carlo was, like, instead of, I think that, the one topic which we were discussing, that the scale up. So I think they are not scaling it up in here. So correct me if I'm
yes, exactly. That was my point. Like on normal dropout, you are scaling the test set, but in this case, I think you are not scaling, but you are using the dropout on the test set, but you have like multiple iterations with different dropouts, and you are averaging the score of each of them.
correct. Yeah, that's my understanding as well. That's what they're saying. And they say that brings about the probability goes down. However, the accuracy get the increased a bit. So if here, like you say, moreover, the model accuracy got a small boost. So it improved in here.
Well, so this literally kind of feels like a ensemble model. Even the accuracy improvement is very similar.
It's interesting. That's why I was asking, have anybody used a Monte Carlo dropout? Because I don't have a much experience, but I haven't heard anybody talking about it beforehand. So that's why I was curious, and that's why we had a good discussion on the point, like how it scaled up and scaled down, and then Monte Carlo was just opposite of what we were discussing. So I'm not sure practicality, or there is any downfall for it, or some.
Yeah, one thing what happens with this kind of techniques, I think that you usually use one of them, and I'm not sure, like I'm totally not sure what I'm saying now, but I think what this thing, it might be not used together with cross validation. Because I think when you are selecting these like final prediction techniques, so it's either like this Monte Carlo technique or like cross validation technique, where you have like a bunch of validation sets and you select one of them. I think what did is like some kind of rules, how you select that you only use like one or another, because otherwise you just get like too much underfitting. But I'm not sure. That's literally just a speculation. What I can.
Yeah, I think that cross-validation and Monte Carlo dropout are just orthogonal things. They are not connected. But you see, the accuracy improvement is really minor. But you have 100 times more computational cost of the inference. I guess that's why it is not so popular, just because it's too computationally costly, you know.
But I think on Kaggle competitions they would not really care that much.
Yeah, but if you have like really deep neural network, you might be not able to run it. But maybe it just doesn't give enough improvement. What I saw in Kaggle competitions, they use an ensemble independently trained models, not this one model just with dropout running. I guess it just doesn't work as good, judging from it's not used in Kaggle competitions. That's my guess.
Yeah, and then I think another thing which he always talk about is like you need especially in the practical sense, like in a medical or finance system, you're probably better off looking at the a bigger picture, as they say, rather than an overconfident model. So if you have the visibility on these guys, like the probability on all different classes, you probably take informed decision. So I'm assuming. So I think it's maybe where accuracy makes sense as far as Kaggle is concerned. However, when you go in a real world, accuracy of 0.01, 0.1,
yeah.
But you always care about the especially in a medical class, like a medical field, just to have a broader picture. Okay, so the last subject was a max norm regularization. I haven't gone through it. I've quickly gone through it, but it sounded to me that it's sort of like gradient clipping. It's a weight clipping. So that's what I gathered from here. It's a regularization trick. But what it's saying is here is that you are going to clip the weights. It contains the weight W of an incoming connection such that W of 2 less than equal to R, where R is the max norm hyperparameter. So what does I gather from here is that what you want to do is whatever weights you have given by the model, they need to be less than the value of R. So I don't have much to say on a max norm regulation.
That sounds a lot like instance normalization, isn't it?
It's like we did a gradient clipping where we just keep them into a certain range between -1 to 1, or perhaps like we did I think norm between mean of 0 and standard deviation of 1, something similar. But this is where we are just doing for the weights. Anybody else want to contribute?
I just again wondering, how does this kind of thing is used with, like, for example, he's even mentioning, like, in this page, he says, like, if you are not using batch normalization, it helps with unstable gradient problems. So I'm just wondering, like, if you are using batch normalization, do you still use like this max norm regularization?
Yeah, so that's a good question. So this is where he has given you some sort of like guidance, a way to start. Like he's saying hyperparameter. So default deep neural net configuration set to start with this, and then I think then if it works, that's fine, and then rest of the here, that's where he's defining, like if you need a sparse model, you can use L1 regularization. If you need a low latency model, then you may need to use a few layers, blah blah blah. So I think this is where he is giving you some guidance whatsoever, but it's not a direct answer to your question. But that's what he said. I think it's more of he's leaving on us to do the experiment, and I guess it depends on your data set as well. Okay, so that's pretty much it from this. Anybody else want to add to I don't, KJ, what's your name, sorry?
Sorry, did you meant me?
Yeah.
Oh, Kazimierz. Kaz.
Kaz, yeah. Anybody else wants to answer Kaz question?
What was the question again?
Well, I just basically said, like, when we talked about max regularization technique, like, do you actually use it with batch normalization, or do you kind of select one or another to use? Because batch normalization, it kind of normalize your outputs, while that max normalization, it kind of normalize your weights.
Yeah, I never saw this max norm used in practice, never tried it. You know, it's just imposes one more constraint on the model weight. So it might work, but I never saw it mentioned anywhere except this book before. So I don't think you need to use it if you are using batch normalization. But it depends on use case. I guess the best way to find out is to try it on different data sets and to get some intuition of how it works and how it combines with other regularization techniques. So I guess you need to run experiments to see actually how it works.
Yeah, and I guess because there are so many concepts in here, and maybe like this NADAM. I heard about Adam. I never heard about NADAM before, and he's suggesting to do an Adam. I have heard Jeremy. I have seen Jeremy using MS Prop or Adam. I haven't seen him talking or using NADAM, but there are lots of concepts in this. Celu is another one. I saw even in this book we have been using Relio himself. He's keeping using Relio, but Celu is one he's suggesting. So I guess you're right. It's more of like do the experiment, look at the data, use different optimizers, activation function different, and then take that away.
Actually, about Celu, I think it's used only in fully connected networks. It's not used in convolutional networks or recurrent networks, and fully connected networks, like vanilla fully connected networks, are not used so often, so Salio is not used so often. I guess that's the reason why we didn't saw it before.
So is there any practical application of the fully connected layers where we use Salio, like for image recognition, we are using more of a conventional neural net? So
yeah, but you can make like you need some last fully connected layers for your output, like for classifier. It's usually made of one or more fully connected layers, and it might be useful there, I guess. And you know, for tabular models, fully connected layers are used. So I guess it worth trying, and we might try it and find out how it works.
Yeah, thanks for that.
And NMS prop, I think it used in, I think it's faster compared to Adam or I think it's faster than Adam, and I think NMS prop it's used in the style transfer. Isn't it?
Yeah, there was a paper mentioned last session in that other group, like not Europe, but regular group on Sunday or Saturday. And that was empirical study of those different optimizers, and they had like a lot of empirical results. I'm not sure. I'll look for this link, and I'll send it to this group.
It's in here. If you go ML, I was looking before coming to this class, so I found that in Joseph. This is the guy.
Yeah.
So if you look at this in here, you'll find this. All right. Actually, we are over quite a lot, so I think I'm going to stop in here. Thanks for joining in.
Okay, thank you.
We'll meet next Wednesday.
Yeah, that's great. Thanks then, Dinesh.
Thank you.
Thank you.
Thanks very much.